Astronomers around the world are buzzing with excitement and confusion after the discovery of a mysterious interstellar object known as 3I/Atlas, an enigmatic visitor hurtling through our solar system. Unlike the countless asteroids and comets that have spent billions of years orbiting the Sun, 3I/Atlas is not bound to our star's gravity. Instead, it appears to have entered our cosmic neighborhood from deep, uncharted regions of interstellar space, and will eventually drift away again after its brief and perplexing encounter with our solar system. This unusual trajectory alone raised eyebrows in the scientific community, but what truly ignited global curiosity were the strange physical characteristics of the object, features that do not fit neatly into any known category of natural celestial bodies, and in some ways mimic the controversies once sparked by the famous interstellar visitor Oumuamua. From the start, astronomers noticed that 3I/Atlas displays a rapid spin rate and an unusual level of brightness, properties that are difficult to explain using standard comet or asteroid models. While typical comets shine simply because they reflect sunlight off their icy surfaces, 3I/Atlas appears to glow with an unusual intensity that does not match what scientists would expect based on the amount of sunlight reaching it. This has triggered speculation that the object might be emitting light on its own through some unknown mechanism. The odd brightness has fueled both scientific and non-scientific theories, with some fringe researchers and internet commentators going as far as to suggest that 3I/Atlas could be an alien craft equipped with an onboard power source. Although most astronomers dismiss such ideas as unfounded speculation, the object's strange behavior does raise genuine scientific questions that have yet to be fully answered. Concerns escalated enough that NASA received inquiries from Representative Anna Paulina Luna and Harvard astrophysicist Avi Loeb, urging the agency to closely monitor the object, especially as it approaches the Sun on Halloween Eve. Loeb, already known for his controversial proposal that Oumuamua might have been an artificial probe, has suggested that unusual interstellar objects deserve more attention, particularly when they display unexplained features. Luna and Loeb expressed fears, however speculative, that 3I/Atlas might somehow deploy mini-probes as it passes near Earth, a scenario reminiscent of science fiction but not grounded in any firm evidence. NASA, while complying with monitoring efforts, firmly denied that there is any threat of an alien invasion or hostile activity. Still, the fact that such a conversation even reached official channels shows how unusual objects like 3I/Atlas can stir both scientific curiosity and public imagination. But while some people lean toward exotic interpretations, other scientists are developing entirely different theories, ideas that could reshape our understanding of how planets form throughout the universe. At the Europlanet Science Congress, Professor Suzanne Pfalzner of Forschungszentrum Jülich presented groundbreaking research proposing that interstellar objects like 3I/Atlas might play an essential cosmic role as planet seeds. This idea suggests that when wandering bodies from interstellar space are captured by the gas-rich, dusty disks surrounding young stars, they could serve as the starting point for building new planets. Rather than being mere visitors passing briefly through solar systems, interstellar objects might actually be the missing ingredient that allows large planets to form far more quickly than previously thought. Planet formation, as traditionally understood, begins with tiny dust particles sticking together through a process called accretion. Over millions of years, these small grains gradually build up into pebbles, rocks, and eventually larger bodies that attract even more material through gravity. But there's a problem. Once particles reach a size comparable to boulders, they tend to bounce off each other or break apart in collisions rather than merging. This bouncing barrier has long puzzled astronomers because it should make it extremely difficult for planets, especially giant worlds like Jupiter, to form fast enough before the surrounding protoplanetary disk of gas dissipates. If planet building relies only on tiny grains slowly gathering more material, it becomes a race against time, and in many cases, the disk should vanish before a planet fully forms. Pfalzner's research provides a potential solution. Her models suggest that if a young star captures an interstellar object, even one only a few kilometers across, that object could act as a ready-made core, a stable, solid mass large enough for gas and dust to accumulate around it efficiently. Instead of starting from microscopic grains, the disk would suddenly have a head start, skipping millions of years of early accretion and bypassing the bouncing barrier entirely. In this scenario, an interstellar object doesn't need to bring anything special with it. Its role as a stable nucleus is enough to accelerate planet formation drastically. Falzner describes this process as a kind of cosmic shortcut, a way for young solar systems to leapfrog the slowest steps of planet building. This idea doesn't just solve the bouncing barrier problem. It may also explain another long-standing astrophysical mystery: why giant gas planets tend to form more frequently around massive stars than around smaller ones. Observational data shows that stars several times larger than our Sun often host Jupiter-sized planets. Yet these massive stars also have much shorter-lived protoplanetary disks. Their disks survive only a couple of million years before dissipating, far too short for traditional accretion models to account for the rapid formation of giant planets. If interstellar objects serve as seeds, however, the process could move at a dramatically faster pace, allowing massive planets to assemble within the narrow window before the disk's gas disappears. Another intriguing element of Falzner's hypothesis is that high-mass stars are more efficient at capturing interstellar objects in the first place. Their strong gravitational pull and large disk sizes give them a higher probability of snagging wandering bodies drifting through space. This means that these stars naturally acquire planetary seeds more frequently, jump-starting the formation of giant planets. Falzner argues that this connection between interstellar object capture and the rapid development of gas giants fits well with what astronomers have observed throughout the galaxy. Systems around more massive stars contain more giant planets, and those planets must have formed quickly, exactly what her model predicts. If Falzner's theory proves correct, interstellar objects like 3I/Atlas could be far more important than previously imagined. Instead of being rare anomalies drifting aimlessly between stars, they might serve as crucial building blocks of planetary systems, helping shape the structure of galaxies over billions of years. Every solar system, even our own, could owe its formation in part to ancient interstellar travelers captured long before the planets we know today existed. The idea that Earth, Jupiter, or Saturn might have originated with the help of a wandering cosmic seed adds a poetic dimension to planetary science. It suggests that solar systems are not isolated creations, but interconnected through the exchange of materials drifting across the galaxy. This perspective also reframes how astronomers should think about interstellar visitors. Instead of viewing them solely as mysterious outsiders or potential alien technologies, scientists may need to study them as fundamental pieces of cosmic evolution. Each interstellar object could contain clues about the environments of distant star systems, the processes that shape them, and the ways in which material moves across the Milky Way. Their compositions, movements, and interactions with other stars might help researchers understand how common planetary systems truly are, and whether life-friendly worlds like Earth exist in greater numbers than we can currently detect. While sensational theories about alien probes attract public attention, the scientific implications of interstellar objects may be even more profound. They provide a rare chance to observe material that formed around other stars, offering samples of chemistry and physics from environments we cannot directly explore. Objects like 3I/Atlas pass close enough to study, but not long enough to capture, making each encounter a fleeting scientific opportunity. Telescopes worldwide rush to gather as much data as possible before these objects slip back into interstellar space, possibly never to return. NASA, for its part, emphasizes that despite the speculation, there is no evidence that 3I/Atlas poses any danger or is artificial. Their monitoring aims to understand its composition, structure, motion, and origin, not to defend Earth from hypothetical alien activity. Scientists expect that as 3I/Atlas approaches the Sun, the increased heat may reveal more details about its surface or internal makeup. If it behaves like a comet, it may release gas or dust, offering clues about what it is made of. If it doesn't, that in itself will deepen the mystery and increase interest in alternative explanations.